No. Okay, let's move on, as Stefan says, to Hans-Martin Hilbig then, who's going to talk about battery life matters. And he's going to provide 3 classroom examples to show us how power consumption can be minimized. So if, Stefan, if you'd like to hand the ball from Franklin to Hans-Martin. Hans-Martin, you now have the ball, so it's over to you.
All right. Thank you, Stefan and Ian. Let me just share my screen and get right into it. Okay, can you see my presentation now?
Not yet.
And then I did something wrong. Let me see. Okay, yeah.
Here we go.
I needed to press one more button.
Yeah, but we have your PowerPoint and now we have your, yeah,
okay,
that's fine.
Cool. All
You're
right.
not in, yeah, perfect. That's perfect.
Okay. So here we go. So welcome everybody to my topic, battery life matters. And at the same time, thank you for Franklin for building me a couple of bridges with his presentation. And I think you could observe this in Franklin's presentation already. If students would learn anything from our presentations here, it would probably be the ability to switch orders of magnitude. So Franklin used, I think, kilowatts at some point in his presentation, but he then also switched down to milliwatts, which is a couple orders of magnitude between. And I think this is probably the challenge that students have to work with when we're looking at energy. Energy is has such a huge dynamic, and this is actually my intro into my presentation here, right? So when we talk at a global level, we see all the energy that is consumed for anything, and so we usually talk in orders of magnitude like kilo, mega, giga, or even terawatts. And so we need to switch gears here a bit with my presentation, because we will actually be in a very tiny world here. But looking at this tiny world with a spyglass, it will present the same challenges that we have in the big world. And for that reason, I think it is absolutely appropriate to have a closer look at tiny electronic devices that are living in the milli, micro, nano, or pico world. So this is what I will be talking about here in my presentation. And in the last 10 years of my professional career at Texas Instruments, I've been working as a program manager for ultra-low energy microcontrollers. So I was very familiar with this micro, nano, and pico world. So milli was already too much and too big for me. So I was more in the domain of micro, nano, even pico. And this is what I would like to maybe share with you here in my presentation. So yeah, we will have a look at the coin cell. I think everybody knows a coin cell from, I don't know, bike computers or any other small powered devices that we use in our day-to-day life. Then we will cover a couple of basics when it comes to the physical measures. And then we will actually go on a safari. We are hunting for an elephant here, and not just one. It's a few more. And so first of all, we will look at is even in this really micro world an elephant, and if we are lucky, we even find a white elephant. And these are those guys that are in the room. Everybody knows them, but nobody talks about them. So let's look not just for elephants, but also for white elephants here. And once we found those, and I guarantee you we will find them, we will look at what can we do to, I don't know, to take a couple of pictures of them, and also what can we do to train them to our benefit. And this is what we will do with our what I call energy lab, which is a lab setup which can be used for a couple of classroom experiments, which I will guide you through later on. So be aware that we are going to be on a mini micro safari here in a minute, and also that we will hunt for elephants, which makes it more exciting, I think, and it also ties nicely into the theme of today's conference. So with this, let me start on the coin cell thing. So I just picked one from Varta, which is a German battery manufacturer. I could also use Energizer or Panasonic or whatever. And the big question here is, how long does the coin cell last actually? And there's only one correct answer. And I'm not seeing the chat window here, but I let you have fun doing your best estimate. How long does a coin cell last? Is it a day? Is it a month? Is it a year? Is it maybe 4 or 5 years? And just to make this thing short here, there's only one correct answer. And this answer is, it depends. So it really depends on what you are using your coin cell for. So to be a bit more precise and quantitative on what this it depends may be, I looked at the Varta data sheet. This is what engineers usually do when they have no clear answer. They say, okay, let's have a look at the data sheet, and then maybe we get some clues about what a coin cell actually can deliver. And looking at the Varta data sheet, which, by the way, I have a link posted at the end of my presentation, we see a couple values here. So we see what they specify a typical capacity. So whatever capacity means here, and I come to this in a minute. So they specify this at 230 milliamp hours, which is pretty interesting, right? So it has the physical unit amps, which is current. It has hours, which is time, and it has milli, which is just the order of magnitude. And these 230 milliamp hours, typical capacity, are measured as a continuous and resistive, a pure resistive load of 5.6 kilo ohms or 5,600 ohms. And the other thing they specify is the time to reach this end voltage of a coin cell, which initially has a voltage of 3.0 volts. So to reach the end voltage of 2.0 volts at a 5.6 kilo ohms load, this takes about 460 hours, which sounds much, right? 460 hours, this is pretty cool. And the typical energy that is stored in this coin cell is 645 milliwatt hours. All right, let's do some math. So first of all, the initial current that is drawn from a coin cell when it's still fresh and young at 3 volts divided by 5,600 ohms is 535.6 microamp. Wow. If we put this into perspective about what Franklin was showing in his presentation, he was talking about milliamps, I can remember, when he was referring to the RGB array. And we say, okay, if we want to have a 19.2 days lifetime of this coin cell, we only need we are only allowed to draw half a milliamp or 535 microamps, to be more precise, at least in the beginning, to come to this 19.2 days of lifetime for the coin cell. So if you say, well, it's good enough to power my RGB array for an hour, well, you're maybe well off with a coin cell, in spite of the fact that the RGB array needs 5 volts as a supply voltage, and the coin cell can only deliver 3 volts. But this might be okay. But if you rather follow the energy consumption reduction theme that we have here in our conference, you say, well, this is probably a bad idea to power an RGB array with a coin cell, because it will shorten the lifetime way below this 19.2 days. And putting this into perspective, this is one of the funny analogies I always like to do here, is think about what you do every day. I don't know, more than one time, I would guess, is do a Google search. As stupid as your search may be, it will consume about 300 milliwatt hours, right? And the typical energy stored in a coin cell is 645. So a little more than 2 Google searches will consume the energy stored in a coin cell. Or to be in a more, I don't know, radical analogy here, you throw away a coin cell for every 2 Google searches, no matter what you search for, right? So this is, I think, something that positions the whole thing when we talk about coin cells here real nicely, right? So we have this order of magnitude switching issue in our day-to-day life as we consume energy. And normally you say, hey, 300 milliwatts is nothing, 300 milliwatt hours. It doesn't cost me much when I come to Franklin's electricity bill. But yeah, it takes me about half a coin cell, which is more than the electricity bill for that milliwatt hours. All right. Now, thinking about this low current flowing from a coin cell, and how can it be that your bicycle computer, for instance, run on a single coin cell for more than a year? So this is really sounds like magic, which in fact is to some extent maybe, but I will uncover this magic for you here real quick. So let's do some math again and do it the other way around and say, hey, how much current am I allowed to consume from my coin cell on a given 230 milliamp hours of capacity to make it last 1 year? It is 26.2 microamps or 0.0262 milliamps, which is almost nothing, right? So for those of you in the audience who are not familiar with working in the microamp range all day long with what they do, 26.2 microamps is awfully low, and normally I would say the average person would probably say, I cannot do anything with 26.2 microamps. But well, bike computers can live there for a life. They can display the time, they can display the actual speed, they can display the number of kilometers or miles you have taken on your bike, and so on and so on. So it is possible, it's just a matter of how you do it. But this now sets the stage, right? So 26.2 microamps is probably a number that you should remember here for the next couple of hours. Now let's switch gears here a little and come to the basics, the basic physics that we have when we talk about battery or energy. So one of the things Franklin already mentioned, this is how is power actually being calculated. It's the product of voltage times current. So the higher the voltage is, at the same current, the higher the wattage is that you actually consume, or the higher the current is at the same given voltage, the higher the power is that you consume. And the difference between power and energy is simply that now another domain comes into play, which is time, right? So power multiplied by time gives energy. And energy typically, at least here in my presentation, is measured in milliwatt hours, or you can measure it in watt hours, and you have to write a couple more zeros and be in a floating point domain. But in milliwatt hours, this is what is normally typical for one electronic device. And to put it in a different mathematic term, which is what I think very, very important. So when you look at it from a math standpoint, you would say energy is the integral of power over time, or the energy of a pulse is actually the integral of its area in a time domain below its power graph. So this is something I guess very, very important to remember, because we now have a couple more choices, right? So we can adjust our power that is consumed, but we also can adjust the time this power is actually being consumed. And this is basically the trick we do in the bike computer to make the coin cell last for a year. And then we have charge. So we go to the old person, Mr. Faraday. I think many of us know Mr. Faraday, and Faraday's formula says the charge is actually on a given capacitance. The charge is proportional to the voltage. So the more voltage you measure on a given capacitance, the more charge is stored in that capacitance. And this is where the battery charging and discharging things come into play. And this is how our today's USB or wall chargers for electrical devices work. And they measure the voltage on a given capacity, and they know what charge is actually in that storage element, which is in most cases it's a battery. And then battery capacity, which we have seen in the VATA data sheet. Battery capacity is a measure of the charge stored by the battery. And it is determined by the mass of active material contained in the battery. So I just read the sentence here for you, because there's a subtle difference between battery capacity and energy, right? So when you look at, again, at the unit, energy or charge, let's compare it against charge, because this is more subtle. So charge is the product current times time, and battery capacity is also the product of current times time. So battery could be charged. It's just a different way. But to really translate this into energy, you also need to put the voltage into account, and then you are in a different domain. And I think, as a measure, we need both domains. We need the milliwatt hours domain as well as the charge or capacity domain. All right, with this, I think we are about ready for our Safari. So as I mentioned a couple of times before, the average current to make a coin cell last a year is 26.2 microamps. So this is my reference here when I look at the system components of this bike computer. So I would like to examine what are the individual parts of this bike computer that contribute to this 26.2 microamp average current to make the coin cell last 1 year. So the most obvious ones are the MCU, which is the microcontroller, which is doing all the computing and also the conversion to drive the display, and also maybe some mathematics. And it's a radio. When you have a bike computer that has a radio link to your wheel sensor, which most of those today's bike computer have, you need to have a radio in this bike computer so it can wirelessly receive the wheel speed information into its system. So these are very familiar and common sense elements as of a bike computer. Then I looked at the data sheets of Texas Instruments MSP 432, which is the same microcontroller the TI hub is using. And I found two interesting current values in that data sheet. One is the so-called active current, which is 80 microamps per megahertz, and standby current, which is 0.63 microamps per megahertz, and not per megahertz, but steadily, when the RTC, which is the real-time clock, is still on. And I'm using this standby current particularly because the bike computer has a time unit inside, so it always needs to monitor the time of the day. So the real-time clock has to be on in this bike computer all the time, even if everything else is on standby. So looking at the average current for the coin cell to make it last 1 year, well, I couldn't even run this microcontroller entirely at 1 megahertz because this would be 2.5 times the average current of this coin cell. So I need to do some tricks here already. And when I look at the radio, this thing really sticks out here big time. And maybe I'm not just fair here with my comparison, but the radio I displayed here is the ESP32, and it has a Bluetooth interface. And the Bluetooth interface needs about 130 milliamps when it's active, and almost nothing when it's in standby, which is good. But the active current of the Bluetooth interface is really high. So it's prohibitive to use this in a bike computer. And this is the reason why your bike computers are not having a Bluetooth radio inside, because it simply consumes too much current. And you need to have a different radio which produces or uses way less current than a Bluetooth interface. The other interesting thing, which we already see when we look at this bike computer, is the display. It needs to have a display at least. And I put three displays here in my example, and I have an LED, which we know as a growth module in our lab setup with the TI Innovator system. We have an LCD, which is used at the bike computer, and we have an e-paper, which you use in your Kindles and ebook readers, if you have those. And let's look at the spec here of those three displays. And when we look at the LED module, we see it consumes 27 milliamps, so it's prohibitive to be used in a bike computer because it would drain my battery real quick. So we can cross this out. Then we look at the LCD screen, and this is more just a proof because bike computers are using LCD screens. They take about 1.9 micrograms active and almost nothing on standby. So this is very nice. So I can leave my LCD display on all the time without eating away too much of my average current for my year lifetime of my coin cell. So that's nice. But then you may say, well, why don't we use e-papers? Because they actually work without any energy. Well, this is true when the e-paper has been written to. So you know this probably from your e-book reader. Even if the battery is totally drained of your e-book reader, it still shows you something on the screen. And this is simply because it shows you the last thing that has been written to the screen. And the bad thing about e-papers is that it takes quite a current to update those e-papers, but it doesn't take any current to, well, keep the display in what has been updated last time. So that's the reason why they are used in ebook readers and maybe price tags in supermarkets and that kind of stuff, because you only update them once per day. But your bike computer needs to be updated once per second when you are riding your bike, because you would like to see your instant speed that you're using, that you are cruising with your bike. So e-papers are not a good idea for a bike computer. That's the reason why. Well, and then we even haven't really seen, we have seen a couple of fat elephants, right? So the LED active is a really visible fat elephant, but where's the white elephant? So there's something. And the white elephant is really the sum of the standby currents that we have here, right? So if you just do the math here, take the standby current of your MCU plus the one of the radio plus the one of the display, then you already have something. And the bike computer doesn't do anything at that time because it's just sitting there sleeping, right? But still, when it sleeps, it eats current, it eats energy out of that coin cell. And I call this the white elephant in the room, because the standby current doesn't do anything good for us, but it drains the battery. So it's something that we shouldn't neglect in our whole system view here. All right, with this, let's quickly go through some other considerations on energy consumption. So in the ideal case, I can simply mechanically switch off any load, and then I have no leakage, and I have only a linear load characteristic, which is the ideal world. But the practical world is actually quite different, right? So even if my TV or my bike computer is on standby, there still is a small amount of leakage draining my battery. And the other thing that makes things worse, I have a nonlinear load characteristic. Okay, so what can we do to reduce the energy consumption? And here's where the variables come into play, right? So I can reduce my power, but I also can reduce the time that power is actually being taken, except for one thing, and this is my white elephant. So the power that is consumed by leakage, or the energy that is consumed by leakage, this will be from beginning to the very end, right? To the end of the battery. And this is something that it's kind of the fixed cost of my energy bill, and I have to give this away. And so it's very obvious to keep this as small as possible. And then I have, well, the actual task of my device, my bike computer in this example. So I have a certain power that is used when I'm measuring the the wheel speed, for instance. And I have some compute tasks to do, like take the wheel speed and transform this into kilometers per hour, as this is the speed we are commonly used to. And I have my famous radio thing here, which we learned takes a lot of energy. So I need to use this wisely and only use it when I really need it, and keep it on sleep every other remaining time. And all these integrals here, they determine the total energy taken off my system. So to summarize what I've been talking about here, you need to minimize the number and the size of the squares, which means you have 4 knobs to turn here, right? So one is the hardware by selecting the right components. Don't use an LED display, use an LCD display in this case. By software, like switch off everything that you can switch off when you're not doing anything, and don't do anything, spend the most time of your system sleeping, and the system architecture, and last but not least, the user. If I have a user who would like to know the instant speed of his bike, I don't know, at a fraction of a second, then I need more measure cycles, I need more compute cycles, and I need more radio cycles. But if 1 per second is okay, well, then it's good. And if somebody else says, well, it's okay if I read my instant speed once per minute, I can actually extend my battery life here. And this is simply the user who determines this. All right, so I need to be careful that I'm not running out of time here. Let's quickly switch to the experiments that I have prepared here to share with you. So I'm using a TI hub, and I'm using a couple of ports here, which you see on the left side of the presentation. So I'm using the analog input to measure the voltage. I'm using a digital output to charge a battery, and I'm using a digital output to control a load circuit. So I have basically 3 modes here. So when charge is on, then, or the BB2 output is high, then the current flows through the resistors, through the diode, into the capacitor, which is a supercap, which is like it's a hybrid between a little battery or a huge capacitor. So when BB2 is high, then this capacitor is being charged. When BB is low and BB3 is low, then nothing happens. The charge in the capacitor is measured by BB5, which is connected to the capacitor. And when I switch BB3 high, then I'm in a discharge cycle, right? So the FET switch turns on, which actually allows current to flow through the LED that I've used here from the capacitor, and so I'm draining the capacitor here by illuminating my LED. Okay, and here you see the piece parts. Don't want to get into detail here. And this is basically the lab setups, or the energy lab, that's how I called it. So here you see the same thing built up on a breadboard. You see the resistors here to actually charge the supercap. You see the Schottky diode, which prevents charge from the supercap flying back into the TI hub. And you see the supercap itself. You see the MOSFET switch and the little LED to actually act as a load for my setup here. So the first task was to characterize the energy leakage of the lab setup, which is more like take a photo of the elephant of my lab setup. So what I did here is I charged the supercap to 2.0 volts or 2000 millivolts, and then I just took record of 1 sample per second throughout 60 seconds to see how my leakage characteristic of my energy setup is. And you see a nonlinear characteristic here, and I was trying to do some regression here. So I used a second order regression, which not quite well fits actually the behavior here. So maybe a cubic, what is it? Order, fourth order regression would work better here, representing the curve here in a better way. Doing the same thing at 1.8 volts, well, we are better off, right? So the scale is different, right? So here, the initial the voltage drop over 60 seconds was 32 millivolts, and at 1.8 volt, it's only 16 millivolts. So the lessons learned here is that the leakage is nonlinear, and the leakage at the capacitor voltage of 2.0 volt is about twice as much as 1.8 volt. So my mode of operation for my lab setup here is probably between 2.0 volt and 1.8 volt to be in a lower leakage domain than going above 2.0 volt. All right, and I'm applying here Faraday's formula as well. It's 0.5 farads times 60 millivolt, which is 8 millicoulombs of leakage, of white elephant leakage consumed when I'm at 1.8 volt versus twice the amount at 2.0 volt. So this was the first task for students to do. The second task is actually to do some experiments here to reduce energy consumptions. So I've provided two Python codes here in the attachment. One is to charge the supercap. So you just define the end voltage, and the time to charge the whole thing is being measured. End voltage, BB3 is switched to high, and no, it's both BB2, sorry. And then you see the supercap voltage increasing here until 2000 millivolts are reached, and the time to charge is displayed. Discharging is a little different. So you define your end voltage, but you also can define the pulse width of the load that you're using. If you put 1000 milliseconds here per second, well, then you have a continuous load. The LED is applied as a load all of the time. And if you only say 500 milliseconds per second, then you have only half of the period the load circuit switched on. And you will see that the battery will last longer. Okay, I really need to work on my time here. The third experiment is rather a combination of the first two, which I call the Discharge Recorder. So again, it will apply the load circuit, the LED, to the charged supercap, but you can provide a couple more variables to the whole thing. So first of all, you can say, okay, how many samples per second will I measure for my discharge voltage, and for how long of a time will I measure these samples per second? And you can define a repetition rate. So is it every second, like the discharge example before, or is it every other second? So the repetition rate here is I have 100 millisecond load pulse every 2 seconds. And then I can look at the recorded data, and I can see, okay, how is energy or charge consumed actually over time when I have a continuous load, which is the blue graph here, versus only 100 millisecond pulse load, which is way lower energy consumption or charge consumption over time. So you can really make up a lot of experiments here by using the Discharge Recorder. All right, last but not least, real quick, how long does an Inspire CX2 battery last? So I think this is a question many of the teachers among you have asked themselves. And I have created a setup to actually measure this. You could sit in front of your CX2, just monitoring it until it dies on the battery, but this is not very professional, I think. So as an engineer, I've created a setup with a second TI hub, which is actually connected to the CX2 TI hub, and it measures whether this guy is still alive. And so as long as this one produces a 0.5 hertz signal, then the monitoring device says, okay, we are still green. The runner here is still alive. And with this, I've measured several setups here. And so the answer, how long does the CX2 battery life last? Again, it's the same thing. It depends. And here's what it depends on. When I'm using black text on a white background and maximum brightness, the whole setup runs about 5 hours, 4 minutes. Doing the same black text on white background, but minimum brightness, I'm actually gaining 1.5 hours of battery lifetime from my CX2. and doing the reverse, like black background, maximum brightness, white text. I'm almost at the same, like the 5 hour, 4 minutes. So brightness really matters, but black background, white text.
Just lost your sound, Hans-Martin.
For me? Come again, Ian. I don't hear
Stefan,
you.
have you an idea what's going on?
I can hear him.
Ah, you can hear him. It's just me.
Go ahead.
Okay. So here's the lessons learned here is actually brightness is a larger factor of battery lifetime, influencing battery lifetime than black text on white background versus white text on black background. But I thought this would be interesting to you. That's the reason why I'm sharing this with you. And you could replicate this in a student setup as well, but don't keep your students in front of the CX2 for this entire battery life. It probably is not a good idea. So with this, I'm running over time here. Sorry about that. Key learnings, you can probably read it yourself. Hope you found the presentation useful for you and inspired you to come with new ideas for your classroom experiments. Thank you.
Thank you very much, Hans-Martin. That was great, most enjoyable, and a nice compliment to the first session from Franklin. I was particularly intrigued by the notion that my mobile phone, of course, can switch its presentation to give me black with white on black rather than black on white, and presumably saving energy. But I have a question for you. If I'm using my Kindle and I switch pages, but I go backwards and forwards, flipping through pages, am I really using quite a lot more energy when I do that?
That's true.
So it's a good idea not to flip pages when using a Kindle. Just open up the page, read it, and then move on to the next page.
Yeah, I think it has a big enough battery to still support
Okay.
the more active page flippers among us.
Okay. Christine, have you spotted anything? I can't see anything in the chat room. Okay. Well, in which case, I suggest. No, you see nothing, Christine?
No, sorry, I was on mute.
Oh, sorry.
Sorry. No, I don't
Okay.
see anything.
Oh, thanks. Thanks for that. Okay. Well.